you will end up with a zygote that is what? In terms of the ploidy. All right, so this is the zygote. This zygote will be 3N, correct? And so what would happen to that zygote?
So that now would be the case where Down syndrome would happen because of this.
I'm glad you say that, Shian, because I'm glad you say that. 1 second, Lourdes. You see this? I said if you have an egg and it is fertilized by a sperm, you end up with 3N. Down syndrome is 2N plus 1. You all agree? Down syndrome is 2N plus 1. 3N is not the same as 2N plus 1. So in a karyotype for Down syndrome, you'll have all normal chromosomes diploid, but when you reach number 21, there is where you have 3. In 3N, the karyotype for a 3N would look like this. You all got that? So usually, if you end up with a zygote that is triploid, it would probably develop into the embryo, but it would always end up in a miscarriage. All right? It will end up in a miscarriage or stillbirth or whatever, but you would never have a human being that is 3N. All right? Is that clear? So,
yes,
like what Lourdes says, the 3N zygote would die, even if it develops into the embryo or into the fetus, and even if that lady gives birth to that triploid baby, it would probably only live a couple of days and then die. All right. So I don't know of any infant or toddler or teenager who is triploid, 3N. I don't know of any. If you all know of any, please let me know so that we can write a book. All right. So if we look at this diagram here, we have primary and secondary non-disjunction. A is a normal X chromosome segregation, right? During the 2 meiotic divisions. So A represents normal meiosis taking place there. But when you look at B, there is non-disjunction taking place in meiosis 1, right here. And so that is referred to as primary non-disjunction when it takes place in meiosis 1. So here you have these chromosomes that fail to separate, all right? And so over here you end up with nothing. And so here you end up with these. Remember, these down here will represent gametes. So for example, I made the example just now of an egg with 2X would be one of these right here. And then the sperm come and fertilize this, and then you end up with a 3N. All right? You can have cases whereby a sperm would come and fertilize this egg, and then you end up with a zygote that is N, haploid. That too would be aborted. All right? And so here you have non-disjunction taking place in meiosis 2. All right? So the first meiotic division went just fine, but right here, in meiosis 2, failure of sister chromatids to separate. And so you still end up with aneuploids. So these would be aneuploids, all right? Cells with an imbalance number of chromosomes, all right? And that can lead to a lot of genetic disorders. All right, so is that understood? So non-disjunction taking place in the first meiotic division would be primary non-disjunction, and in the second meiotic division, secondary non-disjunction. Is that clear? Sex determination and sex linkage in eukaryotic systems. Let's understand how sex is being determined in different organisms, different eukaryotic organisms. Firstly, there is the genotypic sex determination system. When you see this term genotypic, what comes to mind? What do you think plays a key role here? It says genotypic sex determination system. What do you think plays a role in this particular system? Do you think
genes and sex chromosomes?
Say that again, Madison.
Genes and sex chromosomes.
Genes and sex chromosomes. Do you think we as human beings, our sex is being determined by the genotypic sex determination system? So it says here, the genotypic sex determination system whereby the sex is governed by the genotype of the zygote. So the genotype is the genetic makeup of the individual, right? Which would include all the genes and all the chromosomes. So all these things would play a key role in determining the sex of an organism. So the genotype, which is the genetic makeup of an organism, would determine whether it's male or female. So in the case of human beings, yes, our sex is determined with the genotypic sex determination system, and we'll get to that in just a few. Secondly, there is the phenotypic sex determination system, where sex is governed by internal and external environmental conditions. So there are some organisms, and we'll mention them in just a few, whereby their sex is determined by certain environmental conditions. All right? So let's first focus our attention on the first one, which is genotypic sex determination system. So we will look at those organisms whereby their genotype determines their sex. All right? So the sex chromosomes play a decisive role in the inheritance and determination of sex. And this may occur in two ways. So let's take a look at the first way how sex can be determined from a genotypic point of view. Here you have the X chromosome to autosome balance system. So it's a ratio between X chromosome and the number of autosomes, right? This particular system occurs in fruit fly, it's Drosophila melanogaster, and nematodes, right? Ratio of X chromosome to autosomes. So it's the ratio between the number of X chromosomes and the number of sets of autosomes. So sex is determined at the time of fertilization. In this system, the Y chromosome has no effect on sex determination, but is required for male fertility. All right? So in this particular case, if you see a fruit fly and it has a Y chromosome, it does not necessarily mean that that fly is a male. Okay? It does not mean that that fly is a male. I'll explain further and I'll cite some examples whereby we'll get different ratio, and based on the ratio, we can determine what sex each fly is. So sex determination in Drosophila melanogaster. This is the fruit fly that we see right here, right? Female is homogametic and male is heterogametic. But this male here, this XY that you see there, that is not male because of the Y that you see there. All right? That male that is heterogametic is not male because of the presence of the Y. No. The sex of the fly is not a consequence of the presence or absence of that Y chromosome. Right now, this might sound very confusing to you guys, but just hang in there, and we'll clear this up in just a few. XXY fly is male, all right? So XXY fly is female. So you notice the presence of the Y chromosome there, but this fly is still a female. Why? What determines sex here? It's the ratio of the X chromosomes and the autosomes. All right? A fly that has only one X and no other chromosome, if it has no other chromosome, they usually put a 0, right? So this male fly has only one X chromosome and no Y. So the ratio of the number of X chromosomes to the number of sets of autosomes, that is what determines the sex of these organisms. So this table that I have here will help to explain that a little bit better. So here we have sex chromosomes on the first column to the left. Sex chromosomes. The next column would be autosomes, and then the next column would be a ratio between the X chromosome and the autosome, and so it is based on this ratio where you'll determine the sex of the organism. So let's look at the first row. This particular organism has 2 X chromosomes and 2 sets of autosomes. So remember the ratio X to A. So 2X and 2A, 2 divided by 2 will give you a ratio of 1. All right? All fruit flies that have an X to A ratio of 1 are normal females. Normal females. Let's take the other row. This organism has 1 X chromosome and 1 Y chromosome. And they have 2 sets of autosomes. But the X to A ratio would be 1X divided by 2A. That will give you a ratio of 0.5. So all fruit flies that have a ratio of 0.5 would be normal male. And this particular male here would be a fertile male. Why? Because we said in the previous slide that the purpose of the presence of Y is to determine fertility. Check the third one. This particular organism has 1X, but no Y. Then it has 2 sets of autosomes. So that also gives a ratio, an X to A ratio of 0.5, similar to the one just above. But because this one does not have that Y chromosome that confers fertility, this would be a sterile male because of the absence of that Y chromosome. So in fruit flies, the Y chromosome does not determine the sex, but rather determine fertility in males. So if we go further, you you have this particular case of this organism having 3 X chromosomes and the normal 2 sets of autosomes.